Okay, so in this video, we're going to do a few examples where we have basically the idea of at least one failure. Okay, so first example, it's a very classic type example of the alarm clocks. Okay, so a student does not want to wake up late for final exams, so she sets 3 alarm clocks. Assume that each alarm clock has a 10% chance of failing. Find the probability the student makes it to a final exam on time. Okay, so we have alarm 1, we have alarm 2, and we have alarm 3. Okay, and the probability that the first alarm fails, so I'm going to say alarm 1 fails, is 0.1. Okay, same thing for the probability that the alarm 2 fails, and same for the probability that alarm 3 fails. Okay. Okay, so now we want to find the probability that the student makes it to her final exam on time. Well, what does that mean? That means that alarm 1, or at least one of the alarms works, right? So alarm 1 works, or alarm 2 works, or alarm 3 works, or alarm 1 and 2 work, or alarm 2 and 3 work. No need to think of all those different combinations, right? At least one of the alarm works. So that's why this is kind of at least one fails, or at least one works. So in this case, at least one works. At least one alarm works. All right, now whenever you see this at least one, I want us to always think about the complement of at least one, right? So the choices are that 0 alarms work, 1 alarm works, 2 alarms work, or all 3 of them work, right? So if at least 1 works, that means 1 or more, then the complement of that, right? The complement of at least 1 working is that none of them are going to work, right? So 1 minus, remember the total probability is 1, so 1 minus the probability that 0 alarms work. Okay? So 1 minus the probability that none of the alarms work. 1 minus none. At least 1 is 1 minus none. Okay? Whenever we see at least 1, always think 1 minus none. So now I need to know, well, what's the probability that 0 alarms work? Okay? So let's see. The probability that no alarms work. So this would mean that alarm 1 fails. Okay? And alarm 2 fails. And alarm 3 fails. All 3 of those things must happen. Okay? All 3 must fail. All right? Now, assume that the alarms are independent of each other. Why would one alarm be influenced by another alarm? It doesn't make sense. So it's reasonable that these alarms are independent from each other, so we can use the multiplication rule. Let me go and scroll down a little bit. So this is going to be equal to 1 minus the probability that alarm 1 fails times the probability that alarm 2 fails, okay, times the probability that alarm 3 fails. Okay, so now I know each of these things. The probability alarm 1 fails is 0.1. Probability alarm 2 fails is 0.1. Probability alarm 3 fails is 0.1. So in other words, this is basically 1 minus 0.1 raised to the 3rd power. Okay, so 1 minus 0.1 raised to the 3rd power equals 0.999. Okay, so in other words, she has 99.9% chance of making it on time. So setting 3 alarms, it's a great idea, right? She went from having a 90% chance of waking up if she only had 1 alarm to having 3 alarms, having a 99.9% chance of waking up. Okay, all right, next question. So in this one, we have a shipment company. randomly selects crates of chips. Okay, so in this case we have like, all these different crates of chips, and you randomly select, some of the crates. You don't check every crate, and you're checking them for defects. So if a crate has 300 bags of chips, okay, so there's 300 bags of chips in this crate, and if at least one bag has a defect, then the entire crate is rejected. Okay, so if the rate of defects is 20%, find the probability that the randomly selected crate will be rejected. Okay, so find the probability that we will reject a crate. So let's write down what we know. We know that the probability of the rate of defects, so the probability of getting a defect, equals 0.2. We're trying to find the probability, so it says find the probability that a randomly selected crate will be rejected. So we're trying to find the probability that a crate is rejected. Okay? All right. So what does that mean? If a crate is rejected, this means the probability that why do we reject a crate? We reject a crate if at least one bag has a defect, the entire crate is rejected. So at least one bag of chips, right? At least one bag has a defect. Okay? So at least one out of the 300 bags in there, right? So remember, when I say at least one, we think 1 minus none, right? Because there could be 0 bags with the defect, there could be 1 bag with the defect, 2 bags, all the way up to all 300 having a defect. So at least one bag having a defect, the complement of that is none. Okay, so this equals 1 minus the probability of no defects, right? So no bag with a defect. Okay, so at least one is 1 minus none. Okay, so this is 1 minus the probability that bag 1 has no defect and bag 2 has no defect, and ... all the way till we get to bag 300 has no defect. Okay? All right. So now we can use the multiplication rule, right? Each of these bags are independent, and the probability that each one doesn't have a defect should all be the same, right? Because we just have this probability of a defect of being 0.2. So, kind of like how over here we had all of these failures, the alarm failing, and then we could just raise it to the third power because I had 3 alarms. So same thing over here. I'm using the multiplication rule, and I can just raise it to the 300th power. Okay, so the probability of a bag, doesn't matter, all of them should have the same probability of not having a defect. So a bag with no defect, or without a defect, right? Raised to the 300th power because I'm multiplying it by bag 1 times bag 2 times bag 3, etc., all the way to get to 300. Since they're all the same probability, I can just bring it to the 300th power. Okay? All right, so now what's the probability of bag with no defect? Well, the probability a bag has a defect, the rate of defects is 0.2, right? So the probability that they have a defect is 0.2. So what's the probability that they don't have a defect? I can figure this out, right? So no defect, right? So the probability of having a defect is 0.2. So the probability of not having a defect, that should be a complement, right? Should be 1 minus the probability of having a defect. Those are the two options. Either you have a defect or you don't have a defect. So these are complements of each other, right? If the probability of having a defect is 20%, that means 80% don't have a defect. So 1 minus 0.2 equals 0.8. 8 or 80% do not have a defect because 20% do have defects. Okay? All right, so a bag with no defect is 0.8. So I have this equals 1 minus 0.8 to the 300th power. Let's see if my calculator will do this. Raise it to the 300th power. It's very close to 1, right? This 0.8 to the 300th power is really, really small. So my calculator says, well, this is approximately 1, right? So in other words, the probability that a crate is rejected is really likely if there are 300 bags and you're looking for, only one of them to reject the entire crate, and the probability of having a defect in each bag is so high. Okay, so actually before I finish this video, let me just add to this one more element. Say instead of at least one bag of chip being defected means I reject the entire crate. Let's say I were to change it to being 2 or more, then I'll reject the entire crate. Okay, so we still want to know the probability that a crate is rejected. Okay, but I'm only going to reject the crate instead of it being at least 1. I'm going to say 2 or more bags are defected. Okay, so remember we can have 0 bags being defected, 1 bag having some sort of defect, 2 bags having a defect, 3 bags having a defect, 4 all the way up to 300 bags having a defect. And when it used to be at least 1, it was 1 or more, right? But now I've changed the problem so it's 2 or more. Okay, so now you're not seeing at least 1, but you're not going to find the probability of 2 bags defected added to 3, added to 4, all the way added up to 300. That's too much, right? So you're still going to end up using complements here just because it's a lot easier for us to find these two probabilities down here. So I'm still going to end up using 1 minus the probability of having 0 defects, or 1 defect. Okay, so that is the complement, 0 or 1. Okay, so 1 minus 0 or 1. So let's see. I already so I can use my these are these two events. I can use my addition rule for them. So this is going to be equal to the probability of 0 defects, okay, plus the probability of 1 defect. Okay, so I actually already found 0 defects. I'm just going to leave it as we found the probability of 0 defects. Remember, that was up here, no bag with a defect. That was this 0.8 to the 300 power. So I'm going to go and write that 0.8 to the 300 power. But what about 1 defect? How do I find that? The probability of having 1 defect, right? So 1 out of the 300 bags has some sort of defect. So, so this is a binomial type problem where, P is the probability of having a defect, the probability of having a defect is 0.2. All right. And 1 defect, right? So that'd be like x equals 1. And n is 300, right? So I'll use my binomial distribution where I have 300, choose 1, times p, which is p is 0.2, raised to the x power. okay, times q, which would be 0.8 raised to the n minus x power, right? You guys remember this? This is n choose x p to the x power q, or 1 minus p to the n minus x power. All right, and so 300 choose 1 is just 300 actually. I'll leave this to you to solve, but you know, that's the way you could change this problem, make it even a little bit more complicated. You know, by rejecting the crate with even you know, with more possibilities of some bags being defected. So instead of having one bag be defected, saying 2 or more, and then you could go up to 3 or more. You would just need to add on, you know, the complement then would be 0, 1, or 2. 4 or more, the complement would be 0, 1, 2, 3, or 4, or 1, 2, 3. Okay.